The next topic for today takes us back to 90% of all inorganic chemistry can be put into the following categories. We've talked about precipitations. We've talked about oxidations. Today is the day we talk about acids and bases. Acid-base chemistry typically involves transfer of a proton. What is a proton? A proton is a subatomic particle, sure. But when we particle, P-R-T-I-C-L-E, when we talk about protons in terms of acid-base chemistry, the symbol we give it is an H+, because a hydrogen atom has a single proton, and a neutral hydrogen atom has a single proton, single electron, no neutrons. But if you strip away the electron from a hydrogen atom, strip away the electron from that thing, you're left with a single proton, no electrons, no neutrons. So we use this symbol, H+, to be a proton. Why do protons matter so much? Well, because acids are defined as proton donors, and bases are defined as proton acceptors. So it's all about transferring of protons, H's with plus. In this reaction down here, if these are my products, I need to recognize who accepted a proton and who donated a proton. The base is the proton acceptor. This thing went from an NH3 to an NH4+. It accepted an extra hydrogen atom, and coming along with that hydrogen atom was a plus charge. Now this guy is my result of adding a proton to that thing. So this thing must have been my proton acceptor, also known as my base. My acid must be this thing because it donated a proton. It was an oxygen, this is water, oxygen with 2 hydrogens. All of a sudden, this is oxygen with 1 hydrogen. It lost that hydrogen, it lost that proton, it's an acid. So the thing on the right is acid, water is the acid. The thing on the left is the base. Ammonia is the base. Ammonia. That's NH3. When we talk about acids and bases, we also have some slightly confusing terminology. The thing that is the result of adding a proton to the base is called the conjugate acid. The thing that is the result of subtracting the proton from the acid is called the conjugate base. Bases turn into conjugate acids. Acids turn into conjugate bases. So these things are referred to as a conjugate pair. Anytime you're talking about a conjugate pair, it means those two things differ by a single proton, a single hydrogen atom with a plus charge. So water and hydroxide are conjugate pairs. Ammonia and ammonium are conjugate pairs. Today's mission is to be able to identify acids and bases and conjugate acids and conjugate bases. We're looking in the reactants side to label acid and base. We're looking on the products side to label conjugate acid and conjugate base. The thing that loses the hydrogen, H2 becoming 1H, the thing that loses the hydrogen is known as the acid. The thing that takes on an extra hydrogen is known as the base. The acid becomes the conjugate base, and the base becomes the conjugate acid. Hopefully you kind of knew that. You're following along. This is good. Chapter 4 is tough, but we got this. Down here, this guy has no H's, and then he accepts one. He's got an extra H in the end. So this is my proton acceptor, also known as my base. Must make this thing my proton donor. It had 2 H's, and then it had 1. This is my acid. Acid, base. Base turns into conjugate acid. Acid turns into conjugate base. Yep. Okay. Do you remember electrolytes? Hopefully. It was just last week. Hopefully. Some electrolytes are considered strong. Some are considered weak. And some are considered non. Well, let's label these guys. This one is a strong electrolyte. because none of my things, none of my molecules are still connected together. They have all broken apart into separate atoms, separate ions. That's a strong electrolyte. This would be called a non-electrolyte because all four of those things are completely intact. And this one, I hope you're yelling at me, is a weak electrolyte. Three of them are intact, while one of them has fallen apart. Strong means completely dissociated. Non means completely intact. And weak means some intact, some dissociated. But today's theme is acids and bases, and we're going to use that same terminology of strong and weak to mean fully dissociated and partially dissociated. Strong and weak acids and bases also exist. HNO3 is known as a strong acid. So in solution, we've got H plus and NaO3 minus. No, that's NO3 minus, sorry. When we consider NaOH, in solution, that becomes an Na plus and an OH minus. These guys are considered strong because they dissociate completely, and we represent that with a forward-facing arrow only. There are 6 strong acids that you must memorize. I really don't like memorizing. I promise I'm not doing it just to make you have one more thing to do. There are 6 strong acids that you must memorize. You need to know their name and their formula. Hydrochloric, hydrobromic, hydroiodic, HCl, HBrHI, sulfuric, nitric, perchloric, H2SO4, HNO3, HClO4. Those are the 6 strong acids that you must memorize. If something is considered an acid and it is not one of these 6 acids, we're going to call it weak acid. Lots and lots and lots of weak acids exist, but 6 strong acids exist, period. If it's not strong, it's weak, as long as it's an acid. Here are some of the strong bases: sodium hydroxide, potassium hydroxide, barium hydroxide. Any of the soluble hydroxides we will consider strong bases. It does get a little more complicated than that, but any of the soluble hydroxides we will consider strong bases because they dissociate completely in solution. What happens when you add acids and bases together? In general, there's a neutralization reaction. An acid plus a base is going to give you a salt plus water. We almost always see hydroxide as our base, and hydroxide needs to be the base in order for this general pattern to be followed. What do I mean? Hydroxide hooks up with an H from the acid, and that's how the water is created. If you have a base other than hydroxide, water will not be created. So, this general neutralization, this is the molecular equation version, but if we go forward and write a complete ionic equation, in the complete ionic equations we wrote before, we said if it's soluble, split it into ions. What we meant by soluble was, does it dissociate in solution? Well, because we're talking about acids and bases this time, our question is really, is it strong? Does it dissociate in solution? Is HCl one of your 6 strong acids? Yes. Make it dissociate in your equation. Is NaOH one of your strong bases? Yes. Make it dissociate in your equation. Is sodium chloride a soluble salt? Does it dissociate in solution? Yes. Make it fall apart. Does water dissolve in solution? Does it dissociate? No. So our complete ionic equation looks like this, where my strongs are separated and my soluble is separated. Cancel out anything that's common among both sides. Those are spectators. And the net ionic equation is what you're left over with. Anytime hydroxide is the base, you're going to have a net ionic equation. Hydroxide is the base and you're reacting with a strong acid. You're going to have a net ionic equation that looks like this. Write the neutralization reaction for the following. Label the acid, the base, the conjugate, and the conjugate. Okay, I can do that. Acid plus base yields salt plus water. All right. This is my base because I see hydroxide. That must mean this is my acid. Hydroxide is a great base. It hooks up with acid to make water. So it must mean that my leftovers get connected together. It must mean this thing, this piece, is an anion, O2C2H3 minus. It must have a -1 charge because H plus that guy is going to give that neutral compound. So this guy must be a single negative charge. So, Ca is going to hook up with that thing. That's acetate, by the way. But I got to have 2 acetates to cancel out every 1 calcium. So my neutralization reaction is Ca, parentheses, O2C2H3, 2, plus water. But one slight hiccup, that's not a balanced reaction. I need 2 acetates to make that balance. So that means I need 2 acetic acids. That's what this guy is, actually, acetic acid. And I need 2 hydroxides. Yeah. So it must mean I make 2 waters when I do this whole exchange. Yep. So if that's my acid and my base, that must mean this is my conjugate base. Did you yell at me? I hope so. And the hydroxide turns into water. It means that's my conjugate acid. The base becomes a conjugate acid. The acid becomes a conjugate base. Whew, that feels like a lot already. I know. Right, the neutralization reaction for each. We are not going to go through and write the complete ionic equation, but oh boy, that's something you absolutely need to practice. Writing equations is often a stumbling block for students. Make sure that you don't stumble. This is my base. I see hydroxide, I think 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 base. It's all about that base. About that base. About that base? Yeah. Must mean all the other things that I didn't mark are acids. Okie dokie. When you put an acid plus a base, especially if that base is hydroxide, you get a salt plus water. In all of these, we got to figure out what's the salt. I'm going to have some potassium and iodide left over when I create water out of that first reaction. I'm going to have some calcium, and chloride left over out of that second reaction. Calcium is a +2, 2+, and chloride is a -. So when they hook up, you got to have 2 chlorides for every 1 calcium and water. I'm going to have some water for sure. I'm going to have some sodium and some sulfate left over, but sulfate's a 2-, sodium's a +1. You got to make those charges balanced. And finally, I'm going to get some water, and I'm going to have some magnesium and some carbonate. Magnesium's a 2+, carbonate's a 2-, match made in heaven right there. The final 2 steps are to make sure each of these equations are balanced and then label the conjugates. I've got 2 H's, 1 I, 1 K, 1 O. Top equation is balanced. Check. I've got 3 H's, 1 chloride, 1 calcium, 2 O's. Yeah, that's not balanced. How about if I make 2 waters? I've got 3 H's, 4 H's, 2 HCl. I got 4 H's, good. 2 Cl's, good. 1 calcium, 2 O's. Balanced. Check. Next, I've got 3 H's, sorry, bad counting. 3 H's and 2 H's, that's no good. I got 1 sodium, 2 sodiums, that's no good. All right, how about 2 sodium hydroxide? 4 H's on the left, 2 4 H's on the right, 1 sulfur, 4 5 6 oxygen, 4 5 6 oxygen, 2 sodium, balance. And then the last one, 4 hydrogens, 2 hydrogens, that's no good. Now it's 4 hydrogens, 1 carbon, 3 4 5 oxygen, 3 4 5 oxygen, 1 magnesium. Good, golden, Fantastic. Balanced. So then the really last thing to do is label the conjugate. Everything on this side is a conjugate something. I know my handwriting is illegible, but that's a C-O-N-J in all of these things. The acid becomes the conjugate base. The base becomes the conjugate acid. When hydroxide is the base, every single time it means water is the conjugate acid. So it must mean these other things are the conjugate bases. Simple enough? I've thrown a lot at you, I know, but we can do this. Let's do this.